Here are three potential energy functions for the simple case of an object near the surface of the Earth, the more complicated case for an object that's not necessarily staying close to the surface of the Earth. So this works in more general situations, although you'll always want to use this formula because it's much simpler in the case if your object stays close to the surface of the Earth and you're considering gravity as an internal force for the system consisting of the object and the Earth or some other mass. And finally, we've got a spring potential energy function, 1/2 kx squared, if we've got a spring force between two parts of the system. Let's look at now how we can use those in the context of problems. So let's first think about some simpler kinds of situations. We define what's on the right-hand side, or sorry, just the sum of the kinetic energy and the potential energy to be something called the mechanical energy stored in the system. And that's just because it comes up so often that we see these two things added together. So this right-hand side we would call the change in the mechanical energy of the system. In the very common situation where no external forces do any work, we're going to see that for the right definition of the system, oftentimes there are no external forces to be found, or if there are some, they don't do any work. So often we're going to find, we'll see this in examples, the left-hand side is 0. And so in that case, if external forces do no work, then the change in the mechanical energy is 0. And if mechanical energy doesn't change, sometimes people say mechanical energy is conserved, or that's an instance of the conservation of mechanical energy. Here, conserved just means doesn't change. It means it's conserved from the initial state to the final state, so it doesn't change its value. In other words, if one of these is negative, then the other one has to be positive. For example, if the change in potential energy is negative, if the potential energy goes down, then the kinetic energy has to go up because the two changes have to add to 0, and vice versa in that case. So let's see that in several examples. Let's imagine I've tossed a ball straight up and the ball is in free fall but still rising in this case. I've just released it from my hand. And let's take as our system to be the ball plus the Earth and gravity as an internal force between the ball and the Earth. And we'll assume air resistance is negligible. In this case, the only force acting on the ball as it rises up is the gravitational force. So there's no other non-gravitational forces that could do work on the system. My hand is not touching the ball anymore. And therefore, in a trivial kind of way, the net work done by external forces is 0, and therefore mechanical energy is conserved. How does this agree with what we said before? As the ball rises, we already said the potential energy stored in the ball-Earth system increases, and therefore the kinetic energy has to decrease, and of course it does. It slows as it rises up, so the system is gaining potential energy as it loses kinetic energy. And again, the Earth effectively doesn't move, so it's a part of the system we don't have to worry about work's being done on, and it doesn't change its kinetic energy either. The ball is the thing that's doing all the changing in motion. Similarly, as the ball starts to come back down, the potential energy is decreasing. Remember, we increase potential energy as an object goes away from Earth. It decreases as it comes back to Earth, and therefore, if the potential energy goes down, the kinetic energy has to go up because the two changes have to add to 0 if the left-hand side is 0. Let's imagine a third situation. If we were in a situation where air resistance were not negligible, then there would be an external force for that system, just consisting of the ball that was tossed and the Earth with an internal gravitational force. We're considering air resistance to be an external force, and in this case, that external force we're imagining would not be negligible, and therefore the work done by that external air resistance force would be negative because as the object is moving, air resistance always pushes back opposite the direction it's moving, and that's the hallmark of negative work. So, as the ball is falling, for example, these two things don't add to 0 anymore. the change in kinetic energy would still be positive, but it's not quite enough to make up for the fact that the change in potential energy is even more negative. So some of that change in potential energy, only some of it gets realized as a change in positive kinetic energy. The rest is done by, it gets lost to the work that's being done by the external force, in this case the air resistance force. Second example, let's imagine we've got a small mass, maybe a little rock connected to a large asteroid. We're going to imagine the asteroid's kind of like the Earth. It doesn't move by a spring force in deep space. So we've attached a rock to the side of a huge asteroid by a spring, and we're going to consider the mass plus the asteroid to be our system with the spring force as an internal force. And in this case, there is some gravitational attraction between the rock and the asteroid, but we're just going to ignore it. It's so puny unless the asteroid gets as big as the Earth or something like that. Most asteroids, it would be totally negligible. So in this case, we're also going to assume the asteroid doesn't move. It's so massive that the rock is the thing that does all the moving in the transformation. In this case, the spring force, just like the gravitational force in the previous problem, is the only relevant force that might do work on moving parts of the system, and therefore there are no other external forces of substance to do work on the system, and then the left-hand side of this relationship becomes zero because of our choice of system. That means we would say that mechanical energy is conserved. Delta Ke plus delta Pe equals 0. As the spring either stretches or compresses, what happens is the potential energy goes up and the kinetic energy goes down. So you might imagine that I have the spring in its equilibrium, relaxed position, and the rock is attached to it, and I take a bat and I give it a whack towards the asteroid, and the spring starts compressing. In that case, the spring potential energy increases, but at the same time, the little rock is going to slow down, so the kinetic energy of the system will decrease. And similarly, as the spring starts to decompress and speed up as it goes out, back towards the relaxed position, the potential energy stored in the spring will decrease, and that means the kinetic energy has to increase. And that's what happens when you have a compressed spring, and it decompresses as it moves towards its equilibrium position. All right. Our next job is to work on the first worksheet having to do with potential energies, and so we're going to start out with problem number 1, which talks about a ½ kilogram ball being launched upward with a speed of 30 meters per second. That's it's kind of a fast speed, but it's still modest. The ball is not going to go far from the surface of Earth. We're going to choose the system to be everything. And so when I say everything, I mean everything that could possibly be doing work in this situation is going to be included inside of our system, and all the forces that are acting are going to be inside of our system. So in this case, gravity is going to be our only internal force, and so the ball plus the Earth would be our system. Gravity's our internal force. We're going to ignore air resistance and pretend that it doesn't have a big effect in here. So if that's the case, find the maximum height above the launch point that the ball reaches. And I know we could do this using our kinematics knowledge, but here I want us to use one of those work-energy relationships that we learned before. So try that yourself, and we will come back in a second and do the solution together.